Hello guys, back with another power electronics video, and we're going to be dealing with another DC-DC converter today. It's the boost converter, which is one of the most fascinating DC-DC converters because you can step up your voltage. Generally all the regulators which we deal with, like the buck and the linear ones, all step down, which is fine, but here you can step it up, where the inductor plays a very important role. And yeah, that's what we're going to be doing today. And let's just go into the circuit, and we can see that the MOSFET is on the low side, which is different from the buck where it's on the high side, where that's why we need the high side driver in the case of the buck and the buck boost, whereas over here it's a low side one, it's a reference to ground, so we don't need the half bridge driver, the IR2110 this time. And I'll be using something different today. So first and foremost, the input PWM, since we're going to be doing it open loop as always, not closed loop right now, it's the TL494 itself, and the setup remains same as the buck converter. If you want some explanation on these values, you could go and watch that buck converter video. So moving on, the output of the TL494 goes, we still do need a driver since we cannot directly deal with the power side. The TL494 can't source and sink that much current, so we have a different driver here. It's the TC4420. Just go to its data sheet, and yeah, this is the one, TC4420. It's a simple low side MOSFET driver, single MOSFET, and it can drive even more higher currents for the gate, which is very nice. And yeah, it works with 5 to 18 volts, and we're gonna be giving it 12 volts, which is great. And the propagation delay is very less, only 55 nanoseconds, and since we are going to be doing only 50 kilohertz switching, that shouldn't be a problem. It's much higher than needed, and it's just a small 8 pin IC like the 555. You just give your input from the TL494, you connect the ground of that here, then you connect the power supply for your TC4420, and you can take the output and yeah, connect the ground of the power supply here. And one thing here which is important, if you just go down to this test circuit, since this switch is, it's a CMOS based one, it does need some kind of bypass capacitor, which is common. So I've put a 10 microfarad one here. They have shown 4.7. 10 microfarad should be good. It acts as a small reservoir, and 100 nanofarad standard just for decoupling and high frequency noise. So we have that, and yeah, that's the circuit there. As I said, we give the input, take the output from here. These are the decoupling and bypass capacitors, and after that the PWM goes to a power circuit here, which is the actual power boost converter, and our input is 12 volts. As I said before, we're going to be running everything off this single 12 volts. And the inductor, of course, I've taken two 330 micro henries in series, so it becomes 660 micro henry. And after that we give our PWM from the TC4420 to this gate through a 10 ohm, just to limit the ringing and all. And the MOSFET here is slightly different. We're not going to be using the IRFZ44N which we normally use. I'm going to be using the IRFP260N, which is a higher voltage rated one, since the boost, even if we're not going to be boosting beyond, let's say, 25 volts or so, from 12 volts, the spikes, since it's going to be on a breadboard, the inductance will be, parasitics will be playing a big role. They're very nosy. So the spikes, reverse voltage spikes, can go much higher than 30 volts. They can maybe even go 60 volts or so. And the Z44N is only a 55 volt rated MOSFET. So to protect that, we can use a higher rated one. 200 volts should be more than enough, and the resistance is still low, 40 milliohm, which is good. The gate charge though is a little bit high. If we go down here, it does have a gate charge of 234 nanocoulomb, which is a little high, but the TC4420 should handle that. It's good enough. That's why we're using the driver there. But yeah, and the diode also, if you see here, the 1N5819 which we normally use, the short key, that too is rated only for 40 volts. So again, we don't want anything to happen to the diode, so I'm using the more 460, which is not a short key, but nevertheless it's a ultra fast rectifier diode, which is good too. The reverse recovery time is only 15 nanosecond, which is very less, and it's rated for 400 volts, which is much higher than what we need, but it should be fine. And also the current at which it can handle is 4 amps, which is much higher, which is good. So yeah, since we can't really get a short key for more than maybe 50-60 volts, this should be good. So that, and we have the output capacitor, which is 47 microfarad, and the load is going to be a 100 ohm load. So yeah, just design these values using the same boost formulas what we have, the standard ones. So yeah, let's now go to the actual circuit. So we have the circuit here, and I know it does look very messy, even messier than the buck converter one, but that's just because of all these crocodile cables and these probes, which I will show you in a second. So as I said, everything from the 12 volt supply, and there's the TL494 and all of its peripherals to control the duty. We have the pod there, and last time I used the IR2110 module, which I etched for the buck converter. This time, since we're using the TC442, as I said, it's just 8 pin ICs, so directly on the breadboard. And yeah, those are the bypass and decoupling capacitors. The output of that goes here to the MOSFET, and as I said, it's the 260N. So it's a TO 247 package, not the TO 220 standard. And there's the capacitor. You could use maybe like a 63 volt rated capacitor or something, but the only one which I had lying around was this giant 400 volt one, so it should do, not a problem, just that the ESR might be a bit high, which is okay. And these are the inductors, toroidal type ones, so 330 plus 330 in series, so 660 microhenry. And the diode, this is another thing, the more 460, the leads, if you can see, are much bigger than what the breadboard you can insert, so that's why I had to put another set of crocodile wires from there. And yeah, preferably maybe do this on some kind of terminal board or a perf board or something, but yeah, for POC purposes this should be fine. And the 100 ohm load, as I said, is over here, it's kept here. And at peak, which is maybe we could get something like 25 volts or so, it should be dissipating almost 7-8 watts, and this is rated for 10 watt. And of course, since you're boosting the output voltage, the input current is going to increase because the law of conservation of energy still remains. So I'm not going to be running this circuit for too long, since these things, if you run it for too long, the breadboard can even melt because the contact resistance does get a little high. So just a small demo, but nevertheless we should be able to demonstrate that our output voltage is being maintained, and by controlling the duty via the pot we can show the boosting. So let me just turn the circuit on, and yeah, I've turned everything on, the supply is on, the battery is connected, and you can see here I haven't yet connected the drain of the MOSFET to the inductor yet, so we don't have any boosting happening right now. So currently we have only 0 volts since the drain is unconnected, but we can see the PWM here on the oscilloscope. We are at the minimum duty, which is 10%. That's the lowest the TL494 can go. So let's just connect this thing, the drain, and we can start seeing the output volt change. So let me just turn this light on for you, and yeah, let's connect the inductor here, and you can see the output has jumped to the supply voltage. And let's start increasing this. Let's go to say 30% duty, and we have around 15 volts. And let's go a little further, maybe we can go to say 50% duty, and we have almost 20 volts, which is very nice already. And maybe we can go up to 60, let's say. We have 24, which is great. And here the resistor has already started getting a little hot, but yeah, we can go a little higher. The maximum safe limit is, let's say, 80%, so maybe we could show 75 just for a small time. We have already 30 volts, which is, we shouldn't run this for too long since the input current might get very high. But yeah, maybe just for once we could go to 80% duty, and we already have 32 volts, and you can see it's not sagging, it's being maintained, which is the important part here. And yeah, let's go a little lower now. Maybe go back to 20% duty, and yeah, we have around very close to our supply voltage. And yeah, let's go back to 10%, and yeah, we have the supply voltage again and the resistor which is already quite hot. Let me just disconnect this wire here again, since we don't want the breadboard to melt right now. But yeah, nevertheless, the POC was verified. As you saw, we reached a peak of almost 30 or 31 volts, which is quite impressive from a input of 12 volts, which is more than twice. And the load too, it's very hot already. As I said, it was dissipating almost 9 watts, and that's very good. That's a good amount of power. And another important thing is the inductor. If the value is a little less, currently I use 660 microhenry. Earlier I was using a 470 microhenry one. This one, it was a drum type one, and basically at the same 70% duty, my output voltage wasn't going beyond 18 volts. And yeah, I realized it the hard way that my inductor was saturating, so this small core couldn't handle the current which was passing through it. It was basically just acting as a short, like a resistor. So these are toroidal ones, and these are rated for much higher current. So yeah, these guys are not saturating, so that's why you could see how nicely the output voltage went to almost 30 volts. So yeah, this was the boost converter which we used using the TC442 driver and the MOSFET here, the IRFP260N. And yeah, that was the whole setup. And yeah, even though I already said it's quite messy, if you just solder all of these on a single PCB or something, the inductance and all the parasitics, you take care of that in the trace lengths, keep them small, then it will act even better. And maybe you could even push out 35 or maybe even 38 volts from this same setup by changing just these long wires in the breadboard. So yeah, that was the boost converter, and I hope you learned a thing or two, because I surely did. And yeah, thank you.